In this video we're going to look at trigonometry and Pythagoras' theorem in 3 dimensions. Now if we think back first of all to Pythagoras' theorem in 2 dimensions, we know that a squared plus b squared equals c squared, where c is the hypotenuse, which is the side opposite the right angle. C is also going to be larger than a and b. So example 8, find the length of AC to 1 decimal place. So what we have is that AC is the diagonal, obviously from A to C. And we can see that that forms a right angle triangle ADC. So we've got the 2 sides on the hypotenuse. The diagonal is the hypotenuse, so we're going to label it C, and we'll label the other 2 sides A and B. So whenever we're solving Pythagoras' theorem, we always start off with a squared plus b squared equals c squared. And then we fill in our information. So we know that a is 4, so it's going to be 4 squared. B is 8, so 8 squared equals c squared. That's 16 plus 64 is c squared. 80 is c squared. Then to work out the length of c, we do the square root of 80. So c works out to be 8.94. or 8.9 centimetres to 1 decimal place. We should also recall that for right angle triangles we can apply simple trigonometry. Now, up to now it's not been known as simple trigonometry, but in our next video we'll be looking at more complicated trigonometry. But anyway, for simple trig we use the mnemonic SOHCAHTOA to help us remember the formula. So SO is sine theta, where theta is the angle, is the opposite over the hypotenuse. Ka means the cos of theta is the adjacent over the hypotenuse, and toa is the tan of theta is the opposite over the adjacent. So the first letter in SOHCAHTOA, the S, the C, or the T, refers to sine, cos, or tan. The middle number refers to the top of the fraction, and the third number in each 3-letter sequence represents the bottom number or bottom term in the fraction. So example 9, find the value of y to 1 decimal place. What we need to do is label the sides. Well, the sides O, A and H. H is the hypotenuse, which is the one opposite the right angle. So that's the diagonal in this case. The opposite is the angle opposite, or the side opposite the angle. So here's the angle. So the side opposite it is y, so it's going to be O. And then the other side is the adjacent, which is the one beside the angle. So in this case, we have to check the information that we have. So we know the adjacent, and we need to find the opposite. So the 2 sides that we're concerned about are A and O. And the side that we don't care about is the hypotenuse. So if we look at SOHCAHTOA, if we get rid of the ones with H in them, we can get rid of SO and we can get rid of Ka. So what we're left with is TOA. And TOA means the tan of theta equals the opposite over the adjacent. In this case, theta, the angle is 41. So tan 41 equals opposite, which is y, over the adjacent of 9. We can multiply through by 9, and we get 9 tan theta, or tan 41, equals y. And putting that into your calculator, making sure your calculator's in degrees mode, and it'll have a D or a DEG at the top of your screen, we get 7.8 meters to 1 decimal place. Example 10, find the value of theta to 1 decimal place. So the first thing we need to do is label our sides. So the one opposite the right angle is the hypotenuse, and opposite to the angle is the opposite, and beside the angle is the adjacent. So we've O, A and H. If we look at the information that we know the hypotenuse is 11 and the adjacent is 3. So that means that the opposite side is redundant. We don't really care about it. So if we write down our SOHCAHTOA and we get rid of the ones which have an O in it, so that's going to be SO and TOA, what we're left with is k, which means the cos of theta is the adjacent over the hypotenuse. Putting in our information we know, so we don't know theta, that's the one we're trying to find out. The adjacent is 3 and the hypotenuse is 11. So cos theta equals 3 over 11. Now what you'd want to do is kind of divide by cos, but we don't do that with trigonometry. We apply the inverse cos and we get theta equals cos to the minus 1 of 3 over 11. I'm putting that into your calculator, so it'll be the shift or the second function of cos. Again, your calculator should be in degrees mode, so there should be a D at the top of your screen or a DEG, and we get an angle of 74.1 degrees to 1 decimal place. Now we can also apply Pythagoras' theorem in trigonometry in 3 dimensions. The key to 3D questions is to identify the correct 2D right angle triangle and then apply the techniques that we've just looked at, or from M4. Remember that all corners of a cuboid are a cube. The sides meet at right angles, so we may need to use more than one triangle per question. So in this cuboid, we have a number of different right angles that we could show. So if we look at the front face, we've obviously got the base length, the height, and then back along the diagonal. On the side, we could have the depth, the height, and then the diagonal. But we could extend that to 3 dimensions. So if we consider the diagonal of the base of the cuboid, that's going to be perpendicular to the height, and then it would be the diagonal right through the cuboid, and that would be the same for any sides. So example 11, the diagram below shows a box with the top ABCD and the base EFGH. The distances are located on the diagram. Find the distance BH. So BH is the diagonal running right from the bottom corner to the top. And to do that, we'll form the right angle triangle to F and then back through again. So HF is perpendicular to FB. Now what we need to do then is we know the height BF, we need to work out the length HF first of all. So for the side HF, we can use Pythagoras' theorem, where we're looking at the triangle HGF, where the angle at G is a right angle. And we've got A, B, and the hypotenuse C. So we've got A squared plus B squared equals C squared. Filling in the information, we know that we've got 5 squared plus 12 squared equals C squared. So 25 plus 144 is 169 equals C squared. So C is the square root of that, which is 13. So FH is 13. Then to work out BH, again we can apply Pythagoras' theorem, only this time the base HF is our A, the height BF is the B, and the diagonal is our C. So we've got A squared plus B squared equals C squared. Putting in our values, so we've just worked out C, or the length HF, to be 13, so that's 13 squared plus 3 squared equals C squared. That's 169 plus 9, which is 178, is C squared. So C is the square root of 178, or 13.3 centimetres. Part B, find the angle FHB. So FHB is the angle between the diagonal BH and the base HF. So we could draw out that triangle to make it a bit clearer. So we've got our angle theta, we've got 3, we worked this out to be 13 and the hypotenuse to be 13.3. So we can use any trigonometric ratio, but let's label the sides first of all. So we've got the hypotenuse, the opposite, and the adjacent. So because our hypotenuse of 13.3 mightn't be as accurate, because we've rounded it to 1 decimal place, it might be better to use the opposite and the adjacent. So we write out SOHCAHTOA The sides we're not interested in are the ones with h, so that leaves us with TOA. TOA is the tan of theta equals the opposite over the adjacent. So the tan of theta is 3 over 13, so theta is tan to the minus 1 of 3 over 13. Making sure our calculator is in radians, or degrees, so it should have a D or a DEG at the top. And this inverse tan of 3 over 13 gets us 12.99 or 13.0 degrees to 1 decimal place. For a cuboid with sides x, y, and z, the length of the diagonal is given by using Pythagoras' theorem in 3 dimensions, which is x squared plus y squared plus z squared. And we could use that in the above question to verify. So the 3 sides in the cuboid above were 3, 5, and 12. So if we do 3 squared plus 5 squared plus 12 squared and find its square root, we're going to get the square root of 178, which works out to be 13.3 to 1 decimal place as it was before. Example 12, the diagram below shows a wedge in which the rectangle ABCD is perpendicular to the rectangle CDEF. So we've got this base, or the back of the wedge is perpendicular to the base. So we could show a right angle at D and at C. So find the distance AF and the angle DFA. So what we've got is we're going to be looking for this length DF and then eventually the angle leading to that. Now to work out DF, so to work out the distance AF, what we can do is consider this to be the diagonal of a cuboid. So we can do that AF is going to be the square root of 6.3 squared plus 8.7 squared plus 4.8 squared, which is the square root of 138.42, which is 11.765 or 11.8 meters to 1 decimal place. Part B then, to find the angle DFA. So let's draw this right angle triangle out a bit clearer. F is at the bottom, D is at the corner, A is up above. We know the height of AD to be 4.8 and we've just worked out the diagonal to be 11.8. We're trying to find the angle at the bottom, so let's call it theta. So this is a trigonometry question where we need to identify the 3 sides. So the 11.8 is the hypotenuse. The one opposite the right angle, or the angle theta, is the opposite, and beside the angle is the adjacent. We know the hypotenuse, and we know the opposite, so that means we don't care about the adjacent. So whenever we do our SOHCAHTOA, we're going to get rid of the options with an A, so that's going to be TOA and CA, and we're left with SO, and SO is the sine of theta is the opposite over the hypotenuse. So sine theta is 4.8 over 11.8. So theta is sine to the minus 1 of 4.8 over 11.8. And making sure again that our calculator is in degrees mode. So it says a D or a DEG at the top. And putting that into our calculator, we get an angle of 24.0 degrees to 1 decimal place. Example 13, a vertical flagpole TP stands in the corner of a horizontal field QRS. So what we have then is that the flagpole will be perpendicular to the line TQ and will also be perpendicular to the line TS. Find the height of the flagpole. So if we look at the triangle, P at the top, T at the bottom, and Q, we know that PT is perpendicular to TQ. We know the angle at Q is 34 degrees, and we know the base length TQ is 30 metres. And we're trying to find the height. So this is a trigonometry question where we've got the opposite, the adjacent, and the hypotenuse. This time we don't care about the hypotenuse, we don't know anything about it. So whenever we go to our trig ratio, so ka, toa, we get rid of the ones with the hypotenuse, and we're left with toa. So that's the tan of theta. It's the opposite over the adjacent. So tan of 34 is x over 30, multiplying by 30, we get 30 tan 34 equals x, which is 20.2 metres to 1 decimal place. And that was 20.235 to 3 decimal places. So to work out the angle of elevation of P from S, we're going to consider the triangle PTS, and this is our angle of elevation. Now we've just worked out PT to be 20.235, and we know that TS is 15. So we can use our trigonometry to work out the angle of elevation. So we first of all need to label the sides. So PS is the hypotenuse, PT is the opposite, and TS is the adjacent. We don't care about the hypotenuse, it's redundant. So in so ka toa we can get rid of the options with the hypotenuse. So that's ka and so. So we've tan of theta is the opposite over the adjacent. Tan theta is 20.235 over 15, and I've used the three decimal place version so that I have some more accuracy in the question. Theta then is tan to the minus 1 of 20.235 over 15, which works out to be 53.45 or 53.5 degrees to 1 decimal place.